So let's look at an example here. What I've got is a mass, 5 kilograms, in a gravitational field 9.8 meters per second squared. It's stationary up here, 5 meters above this platform that has a spring attached to the bottom of it, and the spring constant is 200 newtons per meter. My question's got 4 parts. First question, what is the GPE at the top here in its current position? Well, our formula, of course, mg delta h, we have 5 times 9.8 times 5, and that is 25 times 9.8, 245 joules. Second question, what is the KE at the bottom? So when this thing falls and hits the plate, what's its KE going to be down here? Well, by conservation of energy, that is to say energy cannot be created or destroyed, we can say the KE at the bottom will equal the GPE at the top. So we can just write down the answer here is 245 joules, just like that. Next part of the question, what's the speed at the bottom? Well, the kinetic energy, as we know, is a half times the mass times the speed squared. So we've got 245 is a half times the mass, which is 5, times the speed squared. So we're going to get here, we're going to have 245 times 2 is 490 divided by 5. That's going to lead us to a speed of just short of 10 meters per second, 9.89 meters per second. So we'll call it 10 meters per second to fit in with the sig figs we've got up here. So the compression of the spring then. Well, again, all of the energy that this thing has, this falling object, is going to become from gravitational to kinetic at this point, and then is going to become elastic potential in the spring. Now we know that the elastic potential energy in a spring is a half force times the extension or compression squared. We don't have the force, but we do know from Hooke's law that F equals K times E. If you remember Hooke's law, we drew a graph of extension against force, and we got a straight line through the origin. So if we put KE in here, we'll get a half K. Sorry, that shouldn't have been squared, my apologies. So the energy is a half FE, it's the area under the graph here. So it's a half KE squared. So we have a half times K, which was 200, times E squared equals the energy that was converted, 245 joules. So we've got 490 over 200 is E squared. So if we take 490 and divide it by 200, and take the square root of that, that's about 1.56 meters. So, what we have done. Question lays out a mass of 5 kilos, stationary, not moving, 5 meters above a platform. The platform has a spring under it with the spring constant 200 newtons per meter. First question, what's the GPE at this point? Well, that's mass times gravity times the height, 245 joules. KE at the bottom, well, by conservation of energy, that's going to be the same as the GPE at the top. We know that because it wasn't moving at the top, so there was no kinetic energy. If it had been falling at 5 meters per second at this point, then we'd have had the energy due to the 5 meters per second here, plus the energy due to the fall from here. And so we'd have had a different answer. But because it was stationary, all of the energy it has here comes from the GPE here. So 245 joules straight off. Question 3 then, what's the speed at the bottom? Well, knowing you've got 245 joules for a mass of 5 kilograms, 245 is a half by 5 by the speed squared, gives us a speed to 10 meters per second, give or take. And then the compression of the spring. Well, that 245 joules is now going to go from kinetic energy at this point to elastic potential energy in the spring as the spring is compressed. And so it's a half force times extension. My apologies for that square, that shouldn't have been there. A half force times extension. We don't know the force, but what we do know is that force is K times the extension, or compression in this case. So we can stick that in there and we get a half KE squared. Stick in our numbers, out drops our extension, 1.6 meters.